Hello and welcome to our review video for D23 water potential. Shh, stop flapping at me. Alright, so the first concept, or the first standard we need to know is what solvation is. Solvation is referring to basically dissolving a solute in a solvent. So our most common solvent is going to be water, so we often will call this hydration. Our solutes can be anything that's polar for water, anything that's polar, or our ions, or ionic compounds. So we dissolve it in there, and then they dissociate into ions. So this is water, right? All we care about right now is water. So water will always move from less concentrated to more concentrated solutions. So you can mix solutions together or put an artificial barrier in front of them, but oftentimes we're referring to cells. So the cell has a solution as well. So it's going to go from hypotonic to hypertonic solutions. That's the direction of water movement. So water is going to move in that direction. Isotonic means water will move in both directions at a balanced rate because it's relatively balanced solutes. And so in this, we're talking about which way water will move due to the relative environments. And so the third standard is talking about cells. Well, it's going to move through osmosis. This is the cell, and you put it in a hypotonic solution, water will go in. So in a hypotonic solution, water will go into the cell because the cell has more solutes than the outside. In a hypertonic solution, water will leave the cell because there are more solutes outside than inside. So we're always talking about the direction of water. So water will move out of the cell in this one. And then in isotonic, right, water will move in and out because you're 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, roughly the same solute concentration. Okay, so hyper, and isotonic. Okay, now for plant cells, we can calculate it. Plant cells. So this is the lab we did. You have a graph of this. On the bottom is concentration of the solution, typically that you put the plant in. Solution plant is in. And this is mass of plant. And then you look to see where it intersects. So this point where it intersects would be isotonic. Oops. Isotonic. Here it'd be hypotonic solution because water is entering. Here would be hypertonic because there's going to be more solutes. So this is the solution that was placed in, and so this right here tells you the concentration inside the plant. So where it intersects is the concentration. Okay. What happens to cells without a cell wall? So in a hypertonic solution, it'll shrivel. Isotonic, nothing will happen. In a hypotonic, it'll burst. Right, burst. And so this is if no cell wall. If there is a cell wall, then you get plasmolysis. So it looks like that. It's shrunk, but it still maintains the shape. Isotonic, it just kind of looks like this. And then in hypotonic, it's like hypotonic, we get turgor pressure. So we need to know those words. Turgor pressure and plasmolysis. Those are words that we use for plants. plants typically want to be at this one. That's what helps them stay upright. Alright, 7 IV bags and bathing organs, right? These are real-world examples of why we care about water potential. Because if you don't, this will burst your blood cells or damage the tissue. So you gotta be really careful about the concentration that you put these things in. And that's the end of the SL content. HL also needs to know the following. We have water potential. So for SL, they only talk really about solutes. For HL, we talk about water potential, which is the potential energy of water. And water wants to move from high potential to low potential. Which makes sense. It's the same as it is for like gravitational potential energy. That's actually standard number 9. Remember for this one here that it is a relative amount. It's always relative to something else. 10. How do we calculate water potential? This probably should not have been the 3rd standard, probably should have been the 1st standard. That's okay. You use psi, the Greek letter psi, so water potential is equal to solute plus pressure potential. Remember that solute potentials can only 0, range from negative, right? But pressure potential can be anything. So solute potential can be negative only because as you add solutes, it lowers the pressure. So the potential. Adding solutes lowers water potential because it's bonding to some of the water and removing its potential to push. Pressure can be positive or negative. If it's positive, it's because you're pushing. Negative if you're pulling through like evaporation. And so you add those together. And so for example, the negative often occurs in the xylem due to evaporation. The last standard, right? We talked about it already, but if you put a plant cell in a hypotonic solution, it'll experience water moving in due to solute potential. Here in hypertonic, the water would move out because it's a higher solute outside, so that means it's a higher pressure inside. So higher water potential here. So this is higher water potential, so water moves out. Here it's lower water potential, so water moves in. Remember, water potential and solute potential are inverses of each other. So as water potential goes up, solute potential goes down. That's super important. Don't forget that.